Good morning. My name is Raffaele Quitadamo, and I'm a PhD student at this university. Today I will talk about my research activity during these 3 years of PhD. And the main topic of my research activity has been strong mobility. That means designing and implementing a migration framework capable of moving threads in the Java virtual machine and from one Java virtual machine to another. The presentation will follow this outline. I'll talk about code mobility and thread migration in Java from a general point of view. Then I will talk about approaches in literature, approaches, application level approaches, JVM level approaches, and my approach. Then I will briefly talk about the JAX RVM, JAX virtual machine, which is the virtual machine, the IBM project that I used in my research. It's an open source project. And then I will go to the design and implementation of mobile JAX RVM, followed by the performance evaluation and application scenarios of thread migration, in particular the 2 application scenarios that I experienced during my stay at HMC in Pensacola, Florida, and the publications. Let's start from the definition. Code mobility is the capability to dynamically reconfigure the binding between the software components and the application that uses these components within a network. This definition leads to a classification of a mobile component from a logical point of view. A mobile component is made up of code segment, data space, which is the objects in the heap, and an execution state. Of course, the code segment is very movable because the byte code has been designed to be movable in the Java virtual machine. The data space is movable as well because it is being designed through the serialization protocol so that it can be moved from one JVM to another using a standard protocol. The execution state instead is not movable right now because it depends on internal structures of the Java virtual machine. For this reason, this motivates the work performed in this thesis. Code mobility can be divided in 2 categories. The first one is weak mobility, which is the most used, the widespread. Weak mobility means that only the data space and the code segment can be moved, while strong mobility means that everything can be moved from code segment, which is byte code, objects referenced by the component, and the execution state, which is a call stack. The focus of this thesis has been on thread migration in the Java language, because strong mobility has been used also in other languages. Strong mobility means in Java that an execution flow, which is a thread in the Java virtual machine, is implemented using some mechanism, some tool, some expedient. From the JVM point of view, I have classified 2 approaches. The first one is called application level approach because the code that has to be mobile, has to be migrated, is instrumented or modified or manipulated at the source code level or at the bytecode level. The other approach is deeper into the virtual machine because we have a modified or extended Java virtual machine, and from within the virtual machine we want to externalize the state of the thread so that it can be moved to another host in the network, for example in a cluster of machines. The problem with this approach is that the bulk of them is only interpreted based, while modern JIT compilers are hardly supported. The approaches have been surveyed and classified. I don't know if you can see this picture, but they range from JVM level, extreme JVM level approaches, and I want you to see that the Nomads approach has been the one that I used also during my stay at HMC because it was designed by Professor Suri at HMC in Pensacola, while the other approaches are bytecode level approaches, source code level approaches. The problem with application level approaches is that the advantage is that they are portable. The disadvantage is that they are extremely slow. They introduce an overwhelming overhead that ranges from 88% to 250%. And preprocessing may introduce security risks because we add hidden instructions into the code. JVM level approaches instead are not portable among JVMs, and they are based on modified JVMs. So the two questions that I tried to answer during my PhD research has been, is portability really an asset? Do we want to have portability and trade it off for speed? And as for the JVM level approaches, are we sure that thread migration is compatible with modern optimizing JIT compilers? Or do we have just to rely upon interpreters? So the research, the objectives of my research has been designing and implementing an innovative Java-based thread migration system approach, and then the system with the target of high-performance distributed systems. I mean clusters of machines on which to run distributed computations, robot coordination algorithms like the one experienced at HMC, or mobile services, which is service-oriented architecture targeted to environments like peer-to-peer managed networks. The architectural features of the framework, which is called mobile JIX-RVM, are fast and complete state capture and restoration, a minimum overhead on the JVM execution performances, and an efficient migration using a JIT compiler. So no interpreters, just JIT compilers, even in presence of aggressive code optimizations. As for the programmability point of view, I try to stay very simple, concise, with an API which is familiar to Java programmers, which is the serialization API. And I try to use a Java virtual machine that is JTK 1.5 compliant, which is very important today. So I chose the JIX Research Virtual Machine, which is an IBM project. It now is an open source project hosted on SourceForge. And it has drawn the attention of many researchers around the world because they found that JIX-RVM is a usable vehicle for research and experimentation on Java virtual machine technologies. We have 150 publications dealing with JIX-RVM, and 4 from my research group, 27 dissertation, and another one is coming soon. And the approach followed is basically a JVM level approach, which means that JIX-RVM has been extended with a code, an extension, which is called mobile JIX-RVM. It was easy to extend because it's written in Java, of course. So the plugin, the component, the mobile JIX-RVM has been written in Java, and it's state-of-the-art with regards to optimizing JIT compilation. This is the timeline of my PhD. In the first year, I've designed the thread restoration and capture in the JIX-RVM and implemented just the version for the baseline compiler, which is the simplest compiler. In the second year, during the second year, I've designed the optimizing compiler extension to deal with code optimizations and allow also optimized methods to be captured by this framework. And I also ported the framework to PowerPC, which is now no more used, but it was just an experiment. And during my last year, I applied mobile JIX-RVM to 2 practical cases, which are the robot coordination with the PIM and the agile computing at IHMC in Florida. And then I made some testing and performance with the couple JVM benchmarks, which are a set of benchmark suite very well known in the community. Let's see what happens when a thread migration. Thread migration means that we have an open stream, which can be an object output stream, and we write a thread object into the stream. This triggers code migration, which means that the stack of the thread is captured, performing a walk back from the last user frame to the first user frame, which is the run method, and the set of physical frames in the stack are converted into a set of logical frames, which means frames at the bytecode level. Thread migration can happen only at precise migration points, which are a subset of JIX-RVM yield points, and the physical stack, like I told you, is converted into a chain of bytecode level Java frames, and the state can be serialized on another Java virtual machine. As from the point of view of the opposite point of view, which is the thread restoration, we have a deserializer thread that opens a stream, an object input stream, for example, using a socket, and reads the state, the chain of frames, and the thread object. It recompiles the method to run the thread again in the target Java virtual machine, recompiles it using a special technique that I've designed during my second year of PhD. So the thread can be started again and continue from the last executed instruction. State capture in JAX-IVM is basically a walk-back process, starting from the last user frame to the first user frame. And there can be three kinds of frame in the stack. We can have baseline frames, which are the most straightforward to capture. The optimizing frames, instead, are very hard to capture, and for this reason they've been treated in the second year of my PhD. And then we have native frames, or JNI frames, which are by definition not capturable because they are C code. So the C code is not portable, is not capturable. The extractor ignores internal JAX frame and uses starts the iterative capture process from the first user pushed frame. So the problem is that, is it possible to reconstruct the bytecode level call stack from the native stack? And, in other words, is the current state of the thread fully observable at any point during the execution? Of course, if we want to have full observability of the execution state, we have to trade off something, because it does not come for free. Baseline frame capture. It's most straightforward. We have a static structure of the frame in the memory, and every variable, locals, stack operands, method arguments is in the frame, in the physical frame. We can have context registers, which is machine registers, but they are only used for the calling convention of the Intel, just to pass parameters from the caller to the callee. And the baseline compiler is the default JIT compiler in JAX, and it just translates, using an iterative process, bytecode into machine code instruction, which is assembly instructions. And no optimization are carried out. So the capture process is straightforward. The state is fully observable by definition, and frame instruction is just retrieves from the physical frame the values of locals, stack operands, and arguments. A bytecode traversal has been implemented to infer the type of local variables and stack operands, because we don't know at some point during execution what is the type, runtime type of each word in the stack, in the frame. So we need to parse the bytecode using a depth-first search approach to determine the locals and stack operands types at a certain program counter bytecode index. And I used also the garbage collector maps to filter uninitialized variables or fake references. Let's go to the optimizing compiler, which is tougher. The optimizing compiler is very complex because it has a chain of subsequent steps. Starting from the bytecode, we go straight to the HIR, which is an intermediate representation, a register transfer-based language that has been used by JAX-IVM for a simple reason, because register-based languages are more effective from the point of view of code optimizations than stack-based representations like in the bytecode. So they translate the bytecode into HIR, which is architecture independent. Then another step translates the HIR into low-level IR, which is architecture independent, but it resembles the instruction set of a RISC machine. That means we have an infinite set of registers to use, which is not true on Intel or on physical machine. And then the last step is machine-level IR, which is similar to the instruction set architecture of the destination, the platform. And during this process, we have a state-of-the-art set of optimization, of code optimization. The most famous are copy propagation, constant propagation, deterministic inline of static non-final methods, and in particular probabilistic inline of visual methods, which has been exploited to capture the execution state. The optimizing frame is very dynamic. There is no static structure except for the frame, which has the basic, the fundamental, essential fields. We have just a spill area and two register save areas, the volatile and non-volatile register save area. This means that the execution state of an optimized method can be scattered among the physical frame and the machine registers. So we cannot know a priori where each local variable or stack operand is physically located. We need some aid from the JIT compiler. That's what I've done. So it's impossible to fully observe and capture an optimizing frame without some aid from the JIT compiler. And it's the price to pay for having execution speeds and performance. Because we can, for example, skip entire blocks of code to optimize the performances. I've introduced a special IR instruction, which is called OSR point. This instruction is treated by the JIT compiler in a special way, in a dedicated way, which means that when the compiler finds an OSR instructions, it builds a map of the state at that bytecode point, and this instruction is updated throughout the optimization process, so that if something happens to a variable, we know it, because in the map this information has been recorded in the map. The final outcome is that, at capture time, we know precisely where local and stack operands have been allocated, either in the spill area or in the machine registers. OSR points, we have to say that they introduce a little slowdown for two basic reasons. The first one is that if we have an OSR point instruction, the JIT compiler is forced to consider all the variables before the OSR instruction live. So it extends artificially the live ranges of variables, which can limit the applicability of some optimizations, like dead code elimination, load store elimination. But this slowdown has been evaluated using the capo benchmark and is very low and reasonable. Thread restoration is instead a different matter. Because during the first year, I tried a physical frame restoration, which means building every stack word physically. This approach, of course, is very simplistic, because it depends on the layout of the stack frame. And if something changes in the layout, we are lost. The second approach, the current approach, is self-installation to specialized prolog, which means that given a frame, the state of the method, and given the bytecode of the method, we can merge these two information into a new bytecode with a prolog and a normal bytecode. Executing the prolog as the effect produces the outcome that the frame is reinitialized at the beginning of the method. So it can be said that a thread restoration is like a fast-forward execution of the past history of the thread, which means that the thread invokes each method in the call stack, rerunning its past history. Performance evaluations have been carried out with the da capo benchmark suite, which is very famous in the JVM community, except then we have also the spec JVM 98 and spec JBB 2000. This suite comprises a set of very diverse applications with the code complexities and memory footprint, different memory footprint. For example, we have a parsers generator, we have an Eclipse application, a SQL relational database engine, we have a Python interpreter, text indexing insertion tool, and Xalan, the XSLT processor. All the reviewed approaches in the literature are very limited and simplistic, because they use recursive algorithms like the Fibonacci or factorization algorithm, just to change the depth of the stack. But this approach, of course, is simplistic, because the capture and restoration time do not depend exclusively on this, the stack depth. There are many factors that has to be considered. First of all, the migration cost can be measured, comprising the time spent capturing a thread, moving a state to another JVM, and restoring that state in another JVM. Then we have to measure the overhead on the JVM runtime, which means how much the thread migration framework may interfere with the normal performances of the Java virtual machine. The last overhead is the overhead on the application execution time. That means what is the price to pay for having strong mobility in a distributed application? If I want to use strong mobility in my distributed application, what slowdown may I experience in the future? These are the times, experience times. The first one, the blue one, is the overhead on the JVM runtime, which means basically that the JVM performs a little bit slower if mobile JAX RVM is installed. We can see that the overhead is very low, that ranges from 0% to 3% for the clips. The green one is the performance evaluation of the application execution overhead. This means that if we want to compile our methods with the optimizing compiler with OSR points, stack maps of the optimizing compiler, we will experience an overhead that ranges from 3% to maximum 8%. So I think it's very reasonable from a point of view of distributed application. These are the capture and restore times. We can see that changing the frame number, the time experienced to capture and restore the stack frame is very limited, especially from the capture point of view, which is in the order of nanoseconds. So it's even less than 1 millisecond. From the point of view of the restoration, we have higher times because we have to recompile the methods each time the thread migrates. But it's still in the order of milliseconds. Mobile JAX RVM has been exploited during my stay at HMC in Pensacola, Florida. HMC is a non-profit research institute, the Florida University System, and is affiliated with several universities, for example, the University of West Florida. I worked in particular with the Nomads team and supervised by Professor Niranjan Suri. At HMC, I have replaced the Aroma VM, which is the Java virtual machine designed and implemented by Niranjan Suri, with the JAX RVM, with my mobile JAX RVM, and applied it to two projects. The first one is the process integrated mechanism, which is the robot coordination using an innovative approach based on strong mobility. And the second approach is instead the second experiment has been the agile computing. Let's start from the PIM. The scenario is the following. We have search and combat operations. We need to coordinate humans, robots, and computers, and we want an easy approach to do this. We have, in the literature, we have two approaches. The centralized approach, which means that we have one single authority, which has a global view of the system, and it can control all the robots in the field and the humans. And this means that we have a low complexity from the point of view of the programmability, but we have a single point of failure, so that if the centralized authority fails, all the system fail. The other approach is the distributed approach, or multi-agent system approach, which means that each robot is run by an agent, a separate agent, and all the agents coordinate through some negotiation protocol or through some shared tuple space or mechanism. And for this reason, we have a high complexity from the programming point of view due to this distributed coordination protocols, but we don't have the single point of failure anymore. Our approach is an approach that tries to balance both the past two approaches, because this model retains the perspective of the single controlling authority, one controlling authority, but the notion that this controlling authority has to be fixed on a node is lost. So we have one single computational state, which is the controlling authority, that moves rapidly among the parts of the system. And for this reason, we need strong mobility in Java. What happens is that the mobile JAX RVM is the runtime architecture platform that runs the PIM. And the single coordinating process is a Java thread that moves from one robot to another in a ring topology. This is an example of 5 nodes with a coordinating process that can jump very fast from one node to another. The idea is that the residency time on each node is very low, for example, 50 milliseconds. And this influences strongly the responsiveness of the system. Why? Because the basic engineering technique that we propose is like an inverse time sharing, which means in conventional computing architecture, we have one processor, single core architecture, one processor, and a number of processes that is scheduled and shares the same processor. In the PIM architecture, we have one process that shares a number of processors. And if the round-trip time of the CP is fast enough, we have the illusion that the same process is running everywhere. So we have to program one CP, one thread, which has a global view of the system, and this thread moves all around the PIM. This is an example of an experiment of this paradigm. We designed, in collaboration with HMC and the Technical University of Prague, Capture the Flag game. The guys from Prague are experts in robot and engineering, so they designed this coordination algorithm, which means basically that we have two teams. They have to knock down the other team and capture the flag on the other field. The red team is run by the PIM. The blue team is run by the multi-agent system in Java. We have the same algorithm, but with two different approaches. And running this experiment, we can see that the robots are moved by the PIM very fast with respect to the multi-agent system because it's more responsive. But the main advantage is from the programmability point of view. If you see the code of the mass implementation, it's much more complex than the PIM implementation. And of course, the red robot will knock the other team down. Agile computing is the last project that I worked on, and it's basically a service-oriented architecture targeted to the needs of managed networks, peer-to-peer networks, where we have limited bandwidth, changing network topology, etc. Service migration is what differentiates agile computing from other service-oriented architectures. What service migration means that a service that is hosted by a server container can be asynchronously stopped, its execution state captured, moved to a new service container, usually on a different node, and then restarted. So we can achieve a set of goals. First of all, the agility goals, which means, for example, that we can exploit new available resources, moving using an opportunistic behavior. The classic scenario is that of an airplane that, and a tank, so that a service that runs on our airplane can move to a tank if the airplane is being attacked, for example. Just consider that these projects are funded by military organizations. So for this reason, we have just these scenarios. To take advantage of better connectivity, for example, co-locality, which means moving the service to the client, nearer to the client, closest to the client, improve resource utilization, and react, for example, to accidental events like a power loss or an incoming attack, survivability. And to implement this architecture, Mobile JXREM has been the execution engine used to achieve service migration. Conclusion. My PhD has focused on strong code mobility in Java. During this period, I've implemented an approach, thread migration approach, that uses JIT compilation and state-of-the-art code optimization. This approach has been implemented and applied to two real distributed computing problems, coordination problem. The IBM JXRVM has been the virtual machine of choice, and several programming language techniques have been used, like the OSR point instruction and the self-installing method prolog to restore thread. The overall approach has been roughly tested with very positive results. For example, we have an overhead on the JVM which is less than 1%, and a slowdown in mobile application code that ranges from 3% to 8%, and the state capture that stays lower than 1 millisecond. The framework, which is Mobile JXRVM, is publicly available, and is an open source project through a CVS server at HMC, and the code is actively maintained and tested on a day-by-day basis. It's now being used in two projects, like I told you, And from a personal standpoint, I have to say that research visit at HMC has been a huge learning and motivating experience, and the collaboration with Professor Suri is going on actively, and I hope it will strengthen in the future. This is the set of publication. Please consider that publications of the work at HMC are still submitted, so they are not included in this list. We are writing several publications with Professor Suri. That's my presentation. And I thank you for your attention.
Thank you very much for
Do you have any questions?
might be the environment of sensor networks.
Yes.
Do you experience
No, but the problem with sensor network is that the hardware of sensor network is too limited, so that we cannot run a JVM on sensor network. Nonetheless, I know that the Sun is designing a special set of sensors that can run a Java virtual machine. They are called, I think, Spot something, and they have better resources. They use the Java virtual machine as the operating system of the sensor. So maybe in the future it would be possible even to use strong mobility. Of course, not with JIX-IVM, which is a virtual machine for servers environments, but with other virtual machine, you can surely have this kind of application.
Other questions? Thank you very much. Your English is really great.
Thank you.